we have already seen the k-means application per se, the R data miner. Now obviously we wanted more information, so let's use this option, that is the k-means algorithm with subspaces selected by entropy weighing. So we'll just click on this. This gives a better output over here. So we're keeping most of the parameters as it is, right, and we're just saying execute. Okay, so we are getting 4 clusters, 5 iterations is what it took, total 6 iterations. And we see the cluster sizes also mentioned over here, that is 175 elements in the first cluster, 201 in the second, 38 and 92. So this is giving us more information than what the first type, that is the capital K and M k-means, was giving us. And you can see this is the means or the average value for the data in this cluster. You can see the cluster centers, that means the individual means. So this is the first cluster, second, third and fourth, and the individual means around that, right? So this would be read as the cluster 1 has 175 rows or elements with the center at 0.3 and 0.34. Cluster 2 has 201 elements with the centroid values for the LSTAT and MEDV transform values as these ones, and similarly for cluster 3 and cluster 4. Now if you want to see this in a better way, let me just draw kind of a grid, or you can say chart, to make sense of this cluster centers over here. So let's assume this is the quadrant based graph with 2 dimensions. So on the left hand side we can have, say, on the y-axis we can assume that we have LSTAT, on the x-axis we can assume that we have the MEDV, right, just for reference. So let's try to plot the first one, that is the cluster number 1 at 0.3 as the centroid value for LSTAT, right? So I'm just doing an imaginary plotting over here. So obviously because it is scaled, so everything is between 0 to 1. So this is 0.3 and 0.34 roughly. This is cluster 2, so let me plot it. So obviously 0.12 will be lower than 0.3, but on the other dimension, so on the MEDV, it will be beyond the halfway mark. So I'm putting it over here with the blue color. So this is this cluster centroid for the second one. Cluster 3, 0.75 high, okay, almost the third percentile, so coming over here, and 0.14, let's change the color, yellow, okay, and the final fourth cluster is 0.48, just less than the halfway mark, and 0.19, the orange brownish color. Okay, so this is how your cluster centroids are placed, almost similar to what we see on the right hand side in the RStudio plot. These are the cluster weights, and these are within sum of squares almost 0, so good cluster. You have the stats over here, so just say yes, so it will install this one time package. So it should give us more information. So I'm just drawing this down. Okay, so the general cluster statistics, 4 clusters, data remains the same as we saw above. This is the minimum cluster size, at least 38 elements in each cluster. The cluster diameter, average distance between the clusters, the median distances between the clusters, separation metrics, a lot of things. And the list continues, so you can just use these things to understand how the clusters are formed. So if you want to look at this from a data perspective, you can click on the data and you can see the plot over there, right? So this is how your clusters are formed, almost identical to the chart we had drawn and also to the previous chart which was present in the RStudio. So this is how your clusters are formed, and you can assume that you have the centered around the same places. This is the discriminant coordinates for the data set. These are how the weights are distributed for the clusters. You have the hierarchical one also. It might not make a lot of sense, but just from a perspective of doing it, we can do it. We have the default mechanism as the Euclidean distance measure, which is nothing but the hypotenuse. So if you have 2 points, and if you draw a right angle, and then you can measure the distance, so you have a formula also for that. You can see the dendrogram for this. You need the ggdendro package for this. Just install it once. So this is how the chart will look. Now this doesn't make sense for data mostly in machine learning, and as you go ahead, this would make more sense when you are in research, specifically the dendrogram and all these things. You have the other techniques also. So a lot of techniques or the distance measurement, but the Euclidean distance measurement is one of the most used one. If you have geological geotag codes, then in that case maybe you might use the Manhattan distance matrix, which is basically not a straight line distance method, but it's using something like how a car goes in New York Manhattan between the blocks, right? So it's not a straight line distance method in that case. So over there that might be used. So when you are using the geotag data, that is where the Manhattan distance measurement is used. Otherwise we mostly prefer the Euclidean, or in certain cases maximum method and so on. This is the default. You can use the complete option also for agglomeration, that is the aggregation. I'm just doing it for the sake of doing. You'll get a better complex chart than what you had seen before, because you have changed the parameters. It's more difficult to observe. So in this data, it's not getting populated for the bicluster. So these are the techniques which you can use within clustering, and that's how you would be doing clustering in Rattle. Okay, so feel free to do more exploration, and more you do, better results you will get.